Hello everyone, my name is Elias and now I'm going to present the research a data-driven approach for neonatal mortality rate forecasting. Well, it's important to know that neonatal mortality is associated with newborn death in the first 28 days of life, and it is considered a relevant indicator for evaluating the quality of care provided to newborns, public health, and the well-being of the population as well as the country's development. According to the World Health Organization, from 1990 to 2019, neonatal deaths decreased from 5 to 2.4 million, but only in 2019, 47% of deaths in children under 5 years old occurred in the first 28 days of life. Therefore, reducing the number of neonatal deaths still remains a major challenge. Thus, reducing infant and neonatal mortality has become a global concern and has been reflected in the approach to the Millennium Development Goals and the Sustainable Development Goals. Specifically, the Millennium Development Goals sought to reduce infant mortality by 2015, and Goal 3 of Good Health and Well-being of the Sustainable Development Goals aims to reduce neonatal mortality to at least 12 per 1,000 live births by 2030. On the other hand, to improve the conditions for decision-making in public health problems, it is possible to use technological advances, and with the historical data stored, it is possible to extract useful knowledge to predict future events. In this context, several algorithms can be applied to the development of time series models, which can capture complex patterns in the available data. Among the models that can be applied are the seasonal autoregressive integrated moving average, SARIMA, also known as the seasonal ARIMA, and even machine learning models. Therefore, the general objective of this article was to present the development of forecasting models in time series using classical statistical techniques and machine learning techniques using real data on neonatal mortality in the metropolitan region of Paraíba River Valley and North Coast in São Paulo state from Brazil. The methodological process of this work consists of a sequence of 4 main steps. The database for this study was obtained from the Department of Informatics of the Unified Health System DataSource, considering the records from January 2000 to December 2020 in the metropolitan region of Paraíba River Valley and North Coast in São Paulo state from Brazil. The collected data were analyzed, the time series was structured, and the monthly neonatal mortality rates were calculated by dividing the number of neonatal deaths by the number of live births per month, expressed per 1,000. In addition, the dataset was split in a 90 to 10 ratio for training and testing, considering rates from January 2000 to November 2018 for training, and from December 2018 to December 2020 for testing. In the literature, classical statistical methods as well as machine learning techniques have been successfully used in time series forecasting. In this work, the SARIMA, random forest, supervector machine, like gradient boosting machine, categorical boosting, gradient boosting, extreme gradient boosting, and multi-layer perceptron models were tested, and their performance were compared in forecasting monthly neonatal mortality rates. And also we identified the stationarity of the series for the SARIMA model and for the machine learning models. And the data was normalized. The model accuracies were evaluated and compared using various error metrics. The model with the best performance was selected by evaluating the lowest values in the error metrics and the highest value in the correlation coefficient. In addition, the predicted rates and the actual rates were compared using the pair t-test to verify significant differences between the values of each model, adopting a significance level of 5%. In the analyzed period from 2000 to 2020, the study area had 697,903 live births and 6,631 neonatal deaths, with an average of 2,7 769 live births and 26 deaths per month. In the time series line graph of the 227 months considered for training, was possible to observe the presence of a decreasing trend in a possible variation of the mean, which may indicate a no stationarity of the series. The results of the augmented Dickey-Fuller and the Kowalski-Phillips-Schmidt-Shinn test for the analysis of the existing of a unit root in the original time series confirmed that the data are no stationary, and therefore a first order difference was applied to the series to make it stationary, especially for the classic series method. The estimations of the best parameters of the Sarima model were performed by applying an exhaustive computational search. Table 2 presents the best parameter configuration of the Sarima model. Likewise, Table 3 presents the best settings for the hyperparameters of the tested machine learning models. The search for the best hyperparameters was performed using a grid search method, in which the parameters selected were those that maximize the performance of the model. The performance of classical machine learning statistical models is shown in Figure 4. The error matrix and the correlation coefficient were calculated by evaluating the difference between the original rates and the rates predicted by the models with the test dataset. The Sarima model presented a low adequacy in the prediction of monthly neonatal mortality rates. From the performance of the machine learning model tested, the categorical boosting, superspectrometry, and gradient boosting techniques presented the best evaluation metrics. Through a visual analysis in Figure 5, the superspectrometry model showed better behavior in forecasting monthly rates, showing a high degree of proximity between the original data and the forecasting values. To confirm this result, a paired test was performed to compare the performance of the superspectrometry categorical boosting and gradient boosting models. The results of the paired test show that the mean of the real data and the mean of the selected models were very close values, so the null hypothesis was accepted for the three models. However, the predictions with the superspectrometry model is closer to the real values, unlike the other models. To conclude, the prediction of future events can significantly help in the reduction of death, as well as in the development of public policies to mitigate risk with preventive care for newborns and improve the system received. In this work, classical models and machine learning models were compared to predict monthly neonatal mortality rates. The classical statistical model evaluated in this work was SARIMA, in addition to the supervised models of random forest, superspectrum machine, light gradient boosting machine, categorical boosting, ingredient boosting, extreme gradient boosting, and multi-layer perceptron. The SARIMA model presented the highest values in the error metrics evaluated compared to the machine learning models. The superspectrometry model presented better precision, demonstrating that it was possible to capture the complex patterns of the data for the prediction of monthly neonatal mortality rates, and these results were reinforced by the paired t-test. Among the limitations of this work is the use of the data provided data source in addition to the comparison of machine learning models only with the SARIMA method. In future work, we intend to compare other classical time series models as well as develop models for predicting mortality rates for the municipalities in the analyzed region. Finally, it is important to highlight that prediction models are not a solution for neonatal mortality. However, they can significantly contribute to the approach of preventive measures for newborn care. That's it. Thanks.